there's a hand microphone on the desk. How do we use the internet?
So this is just, yeah, I turned it on. Sorry for the delay. I'm Gary Geller. This is Mike Abrams. We're with NASA and work in Pasadena, California. So what we're going to do, this is, if you're, just to make sure you're in the right place, this is an introductory class to using remote sensing data or satellite images for conservation. So what we're going to do, I think all of you should have an outline sheet that describes the sort of the three-part program that we're going to do. Does everyone have one of those? Okay. Did you get one? Yes. Okay. And the other thing you need is a copy of one of the data sticks that has been passed around. You should copy that to your desktop if you haven't done that already. Has everyone done that? Does everyone have that folder? It's about 1 gigabyte on their desktop. Everyone good there? Okay. If someone walks in, maybe we'll put a few data sticks in the back table. You guys in the back can nab them and tell them what to do. Okay, now on that, in the home directory of that folder, there's a file called terralook2, something.exe. If you have not already, that's the software that we'll be using a little bit later. So if you haven't already installed that software, go ahead and do it now. And hopefully that'll install without any problems on your machine. It just takes a minute or two to install. Is everyone good with the software? Anyone have any problems with that? Okay, good. So, yeah. Yeah, we're looking for some additional power strips to plug in some of the machines, including the one up here that I'm using on my laptop. So, what we're going to do, this is in 3 parts with a break in between, which will take at about 3:30. And we'll also, Mike will be doing a demo of how to order data. It'll be a live internet-based demo. The internet's very fast here, so it's faster than it is in my office practically. So I think we'll be able to do that. You may actually be able to download some images if you haven't already of one of your favorite sites. And if you've got to work with that, then with the sample images that are on the folder that I passed around, then that's just fine. So the first part of this is really just some background and introductory. I guess I should acknowledge the sponsors. TerraLook is really a collaborative effort between NASA and the U.S. Geological Survey. They're what we call the operational partner. NASA basically built the system, passed it on to USGS, who actually operates the system. So when we order data from the system, it actually comes from the U.S. Geological Survey. There are a bunch of other sponsors as well, including a USAID-funded project called Surveyor. TerraLook was a finalist for the St. Andrews Prize for the Environment, so there was some of the prize money there went to it. Yavin is the Inter-American Biodiversity Information Network. It was a project funded by the World Bank. They funded some work here, as well as the Nature Conservancy and the U.S. State Department funded some of these. So we appreciate their help. So why are we offering this workshop? Well, we find that there are a lot of people doing conservation work who would like to use satellite images, but the systems often that provide those images, or the software that's out there to utilize the images, is kind of cumbersome and sometimes just downright unfriendly. So we're hoping in this workshop to introduce you to some of the methods that are available to obtain data and then to do some conservation relevant activities with it. We'll start by showing some examples of how satellite images have been used for conservation, some very simple stuff. Introduce TerraLook, which is this software and images that I talked about. And then I hope that when you leave here, you'll be just simply more comfortable with the idea that you can use satellite images for some of your work. and hopefully as well have some skills that you didn't have before. So we start with some introductory material, explaining, and Mike will do this, he'll explain where images come from and go through some case studies. We'll talk about some basics of TerraLook, and I think the software's already installed, so we won't do that again. And then in the third section, we'll talk of various ways of working with images and with overlays and some other things that you'll need to know to work with those. Does everyone know where the restrooms are? Go out the door, turn right, turn left, and it's on your right. It's pretty well marked, actually, but you need to know that. We're going to take a break around 3:30-ish. The coffee and cookies come out about 3:30. So it doesn't really matter when we break here. We'll just stop at about the right time. And then I do recommend that you rush out there and grab some biscuits. I'm told they go pretty quickly. I want everyone to have cookies if they want them. Internet is available here, and it's so good, I guess, if you guys lose interest and you want to check your email and stuff, then no one will actually know, except the person behind you. And I see most people have computers. There are a few that are sharing, so I don't see any problems with that. I'm going to do this one. So this is just a few examples of how images are useful, from some very, very simple ones, showing change over time. So here, in this image, in both images, we have the arrow C, which you may know the story here because of agricultural practices, particularly for cotton in this area. The rivers that feed the arrow C have mostly been shunted off into the agricultural fields. So the arrow C has been shrinking very quickly. Here's just an example of that. You've probably seen the pictures of the boats in the sand. So this is a little bit different application. This is in Ecuador near Guayaquil. There's a river that comes out here. This was all originally mangroves, but as probably a lot of you know, mangroves are very popular areas for conversion to shrimp ponds. So in the left image, we should have started a little bit earlier. That image has been what we call classified into two categories. One category is vegetation, which would still be mangroves, and then the other category is shrimp farms. So if we look at this, we see there's a lot of shrimp farms, but at least there's some mangrove left. About 10 years later, there's almost no mangrove left at all. So it's just an example of two things. One, how you can compare images at different times to make a point. And the other, it is possible to classify the images into different categories in this very simple example. This is really a cool poster. Mike put this together. Just different agricultural practices viewed from space. It's neat to look at, and if you're interested in what these are, you can go actually to a website that I can just see me afterwards, and Mike I can point you to that. This is a national park in Thailand called Phu Kardong. Is there anyone here from Thailand? So you're not going to laugh at my pronunciation of the park, which I know is not very good. This is really an interesting image. What this is, you can probably guess where the park boundary is, because that's where the forest ends. This is deciduous tropical forest with a plateau on the top that's a pine savanna. So it's a little bit hard to tell here, but this is, if you start in the ground here where these rice paddies are in some suburban areas, you can climb up here, I think it's something like 1,500 feet, onto this pine savanna, which is these distantly scattered pine trees with grasses underneath for the most part. Now this image was taken at the beginning of the dry season, so the deciduous trees have not yet lost their leaves. If we look at an image, and I don't have one here, but if we were to look at an image later on in the season, this would not be green, it would be more brown, purplish. But on top, the grasses there have already senesced. And so senesced vegetation is typically brown. And you're saying, that's fine, but this is purple in here. Well, as I'll explain later, or Mike will explain, the image, the color it is not generally perfect on these images. However, to understand why it's purple, you can imagine this. So brown has a lot of red in it. Purple has a lot of red in it. And these images tend to have a little bit too much blue. So you take that extra blue, you combine it with the red that's in the brown vegetation, and you end up with purple. So that's why that has sort of a purplish hue. The other thing you can see here is there is green on this plateau. Well, as you might imagine, those are rivers, where along the course of the rivers is live vegetation. But you'll also see this thing right here. And I didn't know what that was until I think it was at the Thailand World Conservation Congress. There was a park ranger there, and I asked her, and she said, well, that's because in the 90s sometime there was a hunter started a fire there by accident. So the vegetation here is quite a bit different than around here, so it looks different. So that's sort of a long-winded explanation of the kinds of things you can see in an image. You can also overlay things onto the image. This is the park boundary. You'll see it doesn't match up precisely. That's actually very common, that the database of the protected area boundary is not precisely the same as what's actually on the ground. There are a variety of reasons for that. You can put down an overlay of the rivers, which you can see the river courses and the trees. These are hiking trails, so the ranger station is actually down here, the information center. You can climb up here and then wander around on the plateau on top. And there is some infrastructure on top. There's another office up here for campers. So that's just some very introductory material. Mike now is going to talk about some of the more nuts and bolts, some of the more technical things about where images come from. You don't actually have to know this, but most people ask that question, so we wanted to give a little bit of background information on that so that you do have some sense of where they do come
from. The next few slides are fairly basic, and we put these together for people who are not very familiar with satellite images. They present some of the basic concepts. I could spend 3 days talking to you about satellite images and image processing and data presentation and data mining, but the whole point of our class here is to provide an introduction. And even if you've never used any kind of image processing software, to allow you to learn how to download images, and then you can look at them with things as simple as Photoshop or Word, even you can display things, or PowerPoint. The images that we download and that the Terralux provides are in JPEG format, which is a very simple format that almost anything can read. So let me go through a few of the slides here. This is what I'll cover, just not in great detail, not at a very high technical level, but just so you get a basic feel for how the data are captured and try to understand a little bit about what makes them up. The advent of digital cameras, I think, is the big, made the big connection between people and it turns out what this technology is. We were using digital cameras in space long before they wound up in your pockets. But now everybody has a digital camera and knows how they work, hopefully. But so images are broken up into little tiny segments. And here's an image with lots and lots of points on it, pixels. Try this one. Yeah. And if we start blowing up the image, so we look at this area larger and larger and larger, finally we get to the point where we see that the image is made up of picture elements. In general, each of these elements was captured by a single detector on the instrument. Your camera has a chip, and there may be 1,000 by 1,000 elements. That would be a 1 megapixel camera. Or the big ones now are maybe 3,000 by 3,000. But so you have 9 million little detectors, and each one captures a part of the image, a little part, and puts it into a regular grid. And then if we back off, we can see that, oh, the grid actually forms an image. So that's basically what we have. It's basically your digital camera, and that's what we're using in space. The cameras operate because the spacecraft moves. We have to capture an image in 2 different ways. One is we have rows of detectors, and the spacecraft moves along, and the row moves along with it, so it's called a push broom. And an older technology was what's called a whisk broom. So you can imagine we have only a single detector, and we pass a mirror, we make a mirror go back and forth, and so it scans the ground, and the image at this point gets onto the detector, and the mirror moves a tiny bit, and the next thing. This is a whisk broom. It's not very efficient. This is a much better way, but this was a more advanced technology. The result is the same. You get an image that's made up of a rectangular grid of points, and that's what the computer uses to produce an image, or you use it. This cartoon I put together to illustrate in very stylized fashion that if you really want to know what's going on with the signal that comes from the ground, you have to know atmospheric physics, you need to know something about chemistry. The sun is the source of the illumination, but the signal that comes up to our little sensor up here comes not only from the reflection from the ground, the grass, but it comes from internal reflections within the atmosphere. The signal from the sun is attenuated by clouds, by various things in the atmosphere like water vapor and carbon dioxide. There are multiple reflections. So it's not as, it can be not as simple as just saying, hey, sun, reflection, I know what I'm looking at. But for many things, just visual interpretation, you don't need to know any of the intervening information. You are comfortable with looking at photographs. So if we give you a photograph or something that looks like a photograph that happens to be taken from space, you should be familiar with it. Vegetation should be green, water should be kind of dark blue. So you're not thrown off necessarily by colors. The thing that may be foreign is the perspective. That is, you're looking down rather than from our little puny vantage point of 5 feet off the ground, looking horizontally. So that's the big conceptual change you have to make, is the fact that you've changed your perspective. What else do I have? The advantage of the kinds of detectors we've been able to develop is that we can detect, we can capture energy in parts of the spectrum that our eyes are not sensitive to. So you all have seen this before. Here's a prismatic through the spectrum of the light broken down that our eyes are sensitive to, from short wavelengths, the violet, through the blue, green, blah, 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 to the red. But this is only a very small part of the possible electromagnetic energy that we have detectors, electronic detectors, that can capture that energy and then allow us to interpret the information that comes from that. So we've grown up all our lives, realizing that vegetation is green, and it turns out it's because vegetation reflects more green light than blue or red, and blue and red energy is absorbed by chlorophyll, so vegetation to our eye looks green. But in fact, vegetation is very bright just beyond where we can see. This is red. In the infrared part of the spectrum, vegetation reflects almost all the energy. So it's very bright in the infrared. And any changes in that brightness are usually related to things like the health of the vegetation, or maybe the nitrogen content or the lignin content. So we can capture that energy that our eyes can't see with photomultiplier tubes of various kinds of detectors. And then we can display that information as an image, but it's something we can't see with our eyes. So there's information in other parts of the spectrum that we have taken advantage of. And a lot of our standard satellites have bands that capture information beyond this part of the spectrum. Another concept, should be familiar to everybody, obviously, spatial resolution, but it's quite important. Here we've taken an image that was captured by I don't know if it was a satellite or an aircraft image, but it was nominally a resolution of 0.5 meter. So that means that every one of the little picture elements was covering a part of the ground that's about 0.5 meter in size. And when you blow it up, you can see, the 0.5 meter. I'm about 0.5 meter wide. So if I were standing there, you should be able to see a little oval thing that was me, but you probably wouldn't be able to see my head. You would just see a single object because the size of the picture element is about as wide as my shoulders. So you might be able, if you were smart, tell that something that was oval shaped and was maybe on a sidewalk was a person, but you'd almost certainly be able to see the shadow of the person. So you would interpret that, oh, I see this shape, I see something dark, probably a person. So that's half a meter. So as you start degrading the image, 1 meter, 2 meters, 5 meters, 10 meters, houses start disappearing. And sort of the characteristic dimension of a building, a single unit habitation, is on the order of 10 meters or less. So already we're starting to lose the ability to distinguish individual structures. So that's a critical distinction for people doing urban mapping and things at the human scale. Sort of 10 meters and less is what you need to be able to see our sort of man-made environment, not big buildings and some roads. When you get up to 20 meters, you know, oh, I guess that's a house, I guess that's a house. That's probably a house that's bright, that's probably a house that's bright. Certainly when you get up to 40 and 80 meters, small structures disappear. So this shows what that looks like. Detectors typically see circular areas, but here's what 80 square